So in this tutorial video about visible light, we'll be looking at the following things. We'll be introducing the idea of the visible light spectrum. We'll be clarifying and confirming some ideas about reflection and revisiting some of the work we did on reflection in Upper 4. We're going to be looking at how the terms transparent, translucent and opaque fit into our current understanding of waves, because these are the terms that we're first introduced to in primary school about waves. We're going to be looking at how filters work in terms of making things look different colours, and we're going to be looking at what's going on when we see objects of different colour. So why do we see some objects as blue? Why do we see some objects as red? As always, remember to use the pause button, make sure you're writing summary notes and bring any questions you have to the next lesson. So previously in physics, we have looked at the electromagnetic spectrum, and we have said that there are sort of 7 named parts to it: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays and gamma rays. And we've said that the radio waves have got the long frequency, the long wavelength and the low frequency, and that is a spectrum, and it gradually changes so that the wavelength gets shorter and shorter and shorter all the way up to gamma rays that have a very short wavelength. And because all of these waves are travelling at the speed of light, they've all got the same speed. If we're decreasing the wavelength from long to short, we must be increasing the frequency from low to high. So radio waves have got a low frequency and gamma rays have got a high frequency. And that is due to the wave equation that we've seen previously of V equals F lambda. Now, we've also previously in the GCSE course started to introduce the idea about where these different waves are coming from, what is generating these electromagnetic waves. And we've previously seen the idea that radio waves, microwaves, infrared, visible, ultraviolet and X-rays are all produced by electrons moving from one energy shell to another energy shell. Okay, so it's the electrons moving between these shells that is producing these electromagnetic waves. And remember, when we were talking about the nuclear topic earlier in the course, we said that gamma radiation, so this is the same gamma from alpha, beta, gamma, yeah? These don't actually come from electrons making jumps or changes in their energy shell. The gamma rays are being emitted from the nucleus of an atom, yeah, as it undergoes radioactive decay, and there are changes within that nucleus. So gamma rays are coming from the nucleus of an atom. The other ones are being emitted by the electrons as they change energy shell levels. Now, when we talk about visible light or the visible light spectrum, we're talking about just one part of the electromagnetic spectrum, this part here. And this is the part of the spectrum that our eyes detect. In the same way that our ears can only hear certain frequencies of waves. And if you look at different animals, they can hear different frequency ranges. Our eyes can only detect the visible part of the spectrum. Now, if we zoom in and look at that part of the spectrum in more detail, this is where we then have our traditional sort of idea of a rainbow and things that we learn about colour and light at primary school. So this idea that we're going from red, orange, yellow, green, blue, indigo and violet. So you might have been taught to remember that as Richard of York gave battle in vain, or another mnemonic. But this is where our rainbow fits in. And actually, what's really important here to take away is the idea that these different colours, that's just our brain interpreting different wavelengths of light, different frequencies of light. So the waves at the red end of the spectrum have got a different wavelength and frequency to the waves at the violet end of the spectrum. And the colours that we see are just our brain's interpretation of those different wavelengths that have been detected. To give you a little bit of an idea about sort of the wavelengths, the size of the wavelengths we're dealing with here, the red end has got the longest wavelength, and we were talking about that again when we were talking about redshift, when we were talking about space physics. This is our longer wavelength, and it's going to have a wavelength of approximately 700 nanometers, nano meaning 10 to the power of -9. Okay, and at the other end, where we've got our shortest wavelength, at the violet end, we're going to have a wavelength of approximately 400 nanometers. So that's 400 times 10 to the power of 9 meters. But really, really important to remember that each colour is its own narrow band of wavelength and frequency. So red has a different wavelength and frequency to yellow, and so on. Now, previously, when we've been studying waves, we've looked at the idea of reflection, and we've seen we've studied reflection off a smooth surface, and we're now going to refer to that as specular reflection. Okay, so specular reflection when we have reflection off a smooth surface. And previously in the course, we've looked at the idea that you can have ray diagrams showing reflection where the angle of incidence is equal to the angle of reflection. We've also learned how to draw wavefront diagrams, and remember the wavefronts are perpendicular to the rays to show reflection. So here's a wavefront diagram of specular reflection. And we also learned how to construct a ray diagram to show how an image is formed in a mirror, which is this one over here. And remember, here's our object. There are rays of light coming from that object. They're being reflected in the mirror, and so we form an image over here. So these are all examples of specular reflection. That's reflection from a smooth surface. Now we're going to just name and remind ourselves that there are other types of reflection that can take place, and we can have also diffuse reflection. So this is where we have reflection from a rough surface that causes scattering. So you can see here this surface isn't flat, it isn't smooth, and so when an incident ray lands on the surface, it gets scattered in different directions. Now what's important to note here is that the incident rays are all actually parallel, but the reflected rays are going off in different directions, but they're all still following the law of reflection. If we draw the normal into the surface here, angle I is still equaling angle R. It's just that the normals are pointing in lots of different directions. So this is diffuse reflection off a rough surface. Now, some other terms that we learnt about light and about visible light when we were younger were the terms transparent, translucent and opaque. And what we're going to do now is we're going to weave those ideas into this kind of more advanced model of visible light. And we're going to link them with some ideas that we've seen previously in the GCSE course about what happens when any type of wave meets a boundary between two materials. So let's have a look to start with our glass block experiment. So this is an experiment that we've all done. We put our glass block on a piece of paper, and we got a ray box, and we shone a ray of light at the surface of the glass block. And what we saw was that a small amount of the light was reflected, and then some of the light was transmitted through the glass block and then refracted out the other side. Okay, and we've got a ray diagram sort of zoomed in of that here. Here's the air, here's the glass. So we've got our incident ray. Some of it's been partially reflected and some of it is transmitted as the transmitted ray. And we said we had this big overarching idea, and we used it when we were looking at ultrasound waves, echo sounding, exploring the earth with seismic waves, that at any boundary between two materials, waves can be reflected, transmitted, or absorbed, and if they're transmitted, they may well be refracted. So let's try and sort of put that idea in with transparent, translucent, and opaque. If we've got an object and we're going to see it with visible light, our eyes are going to detect the visible light that's interacting with that object. If the waves that are incident on it are reflected back or they're absorbed, then we say that that object is opaque. Okay, so if none of the light is being transmitted through that object, it's an opaque object. Okay, so we can't see through it because the light isn't transmitting through it. If, on the other hand, we've got an object that does transmit light, then we can say that that object is either transparent or translucent. And you might remember that when we're talking about transparent, we're saying we can see through it clearly. And when we're talking about translucent, we're saying that light is passing through it, but we can't see a clear image. And we can then link that to how much refraction is taking place and how smooth the surface is. Now, next, we're going to talk about how colour filters work. So a colour filter is a piece of material that you can look through, so it's transmitting some wavelengths, but it makes objects look a different colour, okay? So the big idea here is that we're absorbing certain wavelengths and transmitting other wavelengths. So I've got a screen video from a FET simulation. They've got lovely simulations, so go and check them out and have a play with them after the video, and we'll have a little look at what's going on. So here I've got a torch that's showing white light, so that's actually all of the different wavelengths together. Yeah, when we see all of these wavelengths in the visible spectrum, our brain interprets that as white light. If I put a filter in front of it, so let's say I've got this blue filter here, that blue filter only lets the certain colour wavelengths go through. So here's a red filter only letting red wavelengths through. It's absorbing the other wavelengths, okay? If I now change the wavelength of my light that's passing through, a red filter will let red wavelengths through. But if I now change that to a different colour, so let's say I've got yellow wavelengths, that red filter will absorb those wavelengths and won't let that pass through. And then if there aren't any wavelengths getting through, my brain is interpreting that as black. Okay, so here I have got a blue filter with blue wavelengths being shone at it, and I'm seeing that as blue. Now we've got the end of the video. So, filters only let certain wavelengths transmit through, and they absorb the other wavelengths. And whichever wavelength is transmitted through and detected by your eyes, that will be the colour that you see. So that's how those colour filters are working. One final point to sort of point out is if you took white light, which was made up of all of the different wavelengths, you pass it through a red filter. So it's absorbed all the wavelengths apart from red. So you then just have red wavelengths carrying on. If you then try and pass those through a different colour filter, like a green filter or a blue filter, that filter will then absorb that red light, and then you'll have a situation where you've got no light being transmitted at all. So you can use different combinations of filters to achieve different results. So the final part of this topic that we're going to discuss is just to go over and confirm again how we see colour. So why do different objects look different colours? Now we first started looking at this in upper 3, but we're hopefully now that we've sort of completed 5 years worth of physics, it's really going to make sense. So if some of these ideas are reminding you of previous lessons when you were younger, that's good, but hopefully this will just confirm it all nicely. So when we see different surfaces and different colours, we're going to be talking about opaque objects now. So if we're talking about, is it reflecting, transmitting or absorbing light, in this situation, some of the light will be reflected and some of the light will be absorbed, but it's not being transmitted. Okay, so let's have a look at this first situation here. Why does a blue object look blue? Let's say that we're shining white light, so that's all of the different wavelengths on this blue object. A blue object is going to absorb all the other wavelengths apart from blue, but it's going to reflect the blue wavelength into our eye. That means our eye only detects the blue wavelength, so our brain interprets it as blue. So all the wavelengths are incident on the surface, the blue wavelength is reflected, and the other wavelengths are absorbed by the material. Let's have a look again at the situation for a red object. White light is incident on the red object, so that's all the different wavelengths in the spectrum. Red light is reflected by the surface and we detect that in our eye, so we interpret it as red, but all the other wavelengths are absorbed. And then we've got the same situation for green light here as well. But really important to remember that if our brain detects all the wavelengths in the visible light spectrum, it's them all combined together, it sees that as white light. Okay, so just to confirm the situation as well, if we're seeing an object that looks white like white paper, all the wavelengths are incident on that object, and it's reflecting all of the wavelengths into our eye, and so our brain interprets that as white. And if you had a black object, all the wavelengths of light are incident on that object, but it's absorbing all of those different wavelengths, so none of the light is being reflected into your eye. Now, hopefully some of you are asking, why do the materials reflect different wavelengths and not others? And if you are asking that question, you need to take A-level physics, and you might even want to think about studying material science, because it's the properties of the material that determine which wavelengths are being absorbed. And it's a lovely crossover between chemistry and physics in terms of how that solid is, what type of bonding is going on that solid, what the electrons are doing, why it's absorbing some wavelengths and reflecting others. So go and study physics A-level, and maybe if you want to, chemistry as well. So that brings us to the end of our visible light tutorial video. Just to sort of go over this, we've been talking about the visible light spectrum and defining that. We've been talking about specular and diffuse reflection. We've fitted in the ideas of transparent and translucent and opaque objects from when we did science lessons when we were much younger to our current understanding of transmitting, absorbing and reflecting. We looked at how filters can make light appear different colours, and we talked about how we can see the colour of different objects based on which wavelengths are being absorbed and which wavelengths are being reflected into our eye and detected. Make sure you've written your summary notes up. You can go back and watch the video again if you need to, but there are so many more interesting areas that you could do some extracurricular reading on this topic. Go and have a little look what you can find. Why do some objects look metallic? Why have they got that shiny lustre to them? Why do objects absorb blue wavelengths and not red wavelengths? So go and do some extra reading around the curriculum, and I will see you in the next lesson.